Bismillahirrahmanirrahim. Greetings. In this lecture and a few more to follow, I am going to discuss about partial sum of some selected series, infinite series. The partial sum, I mean finite part of them, and come up with some kind of mathematical formula. Now, a series like 1 plus 2 plus 3 plus 4 and so on and so forth plus n. And or series like 1 square plus 2 square plus 3 square and so on and so forth plus n square. Series like 1 cube plus 2 cube plus 3 cube and so on and so forth plus n cube. This kind of series I'm going to go over. Now, I start for today's lecture with the first one, which is 1 plus 2 plus 3 plus 4, and so on and so forth up to n. So let's get started for today's lecture, shall we? Now, suppose we are asked to add 1 plus 2 plus 3 plus 4 up to, let's say, 100,000. Or maybe 1 million. And we know that is not practical. We sit and add and add and add. If you don't know any other operation, it takes you a whole few days. And the longer it takes, there is more chance for making mistakes. So we have to seek for some kind of pattern, some kind of hint in there, so that we may come up with a faster to do that, not to go through all this laborious job of adding and adding and adding. What we know about multiplication is that multiplication speeds up the process of addition. So multiplication is repeated addition in reality. So knowing that one, we see if there is a way we can change 1 plus 2 plus 3 plus 4 up to 100,000, if we can change them into some kind of multiplication so that we can speed up the process of repeated addition. So what we do, we cut part of this long chain of addition. Let's say we go from 1 to 5. 1 plus 2 plus 3 plus 4 plus 5. And we look to see what kind of simplification we can come out of it. We have in mind to come up with some kind of multiplication. You follow me so far? So we notice that number one, that the numbers are kind of symmetric in a sense. Like 1 and 3 are symmetric and the middle of them is 2. Some kind of symmetry is between the numbers. The other thing we think is contemplating. The other thing we notice from 1 plus 2 plus 3 plus 4 plus 5 is that the distance between any two successive terms remains same. In this case is 1. So this is two observations we made. Then taking the kind that we noticed first, that is symmetry, we know that 1 plus 5 is 6. 2 plus 4 is 6. 3 plus 3 is 6. So we have 3, 6. Now I have played with this, and we can come with the formula, with the same formula that I'm going to discuss it shortly. But there is another way to do it, which is kind of more comprehensible for the beginner students. So I go and demonstrate the second technique in a sense. But what I just said can lead us to that general formula. It takes about 5-10 minutes to go over that, explain it, but I bypass it if I may. Now what we notice from 1 plus 2 plus 3 plus 4 plus 5, if we take this chain and rotate 180 degrees in a sense and put it next to each other under that, So 1 plus 2 plus 3 plus 4 plus 5 becomes 5 plus 4 plus 3 plus 2 plus 1. Line them and add them. So you get 6 plus 6 plus 6 plus 6 plus 6. 5 sixes. Hooray! Lo and behold, we did come from addition into multiplication. Isn't that fantastic? That was our goal was. So we have 5, 6. So 5, 6 is 30, but the goal was to add from 1 to 5, not the mirror image of that, to add them together. So no problem. 5 times 6, 30 divided by 2. It's fantastic, isn't that? So seems like we have come to a formula. Now, then question to ask is, how do I know it works for 6? You went from 1 to 5, what about if you go 1 to 6? If we do that, we come with the same. So we come, write it 6 under 1, and 5 under 2, and so on and so forth, and you come with 7 plus 7 plus 7 plus 7, 6 sevens. So 6, 7 divided by 2 is what we were after, which is 1 plus 7. Now then, you say, how do I know this will work for 8 and 9? How do I know it works for 9 and 10? How do I know it works for 1000 and 1001? I know it works for 6 and 7. How do I know it works for that? And that is what the mathematical induction comes into the picture, and mathematically proves that yes, it does work for all the given natural number. In other words, when it works for 5, the mathematical induction shows that it does work for 6. Not that it works for 6, mathematical induction shows it does work also for 7. Not that it works for 1000, mathematical induction says it does work for 1001. So that guarantees us that from 1 to 100,000 that we started initially, we have a formula. And the formula is n times n plus 1 divided by 2. Do not memorize formula, do not follow any kind of recipe. So remember 1 plus 2 plus 3 plus 4 plus 5 is, you put it the other way, become how many? 5 times 6, then divided by 2. So 5 times 6 divided by 2 is n times n plus 1, because 6 is 5 plus 1. So n, which is 5, n times n plus 1 divided by 2. Do you follow me? Now, then the question comes, can we apply this kind of observation to next series, which is 1 squared plus 2 squared plus 3 squared and so on? Can we apply the same for 1 cube plus 2 cube plus 3 plus 4 cube and so on? The answer is that they are not symmetric, and the distance between the successive terms is not going to be constant. It's not going to be the same. So the procedure that we used for this one, 1 plus 2 plus 3 plus 4 and so on, will not work for others. Now, the point is that we are going to develop a formula, a technique, a strategy that will work for all of them. 1 plus 2 plus 3 plus 4 and so on, 1 squared plus 2 squared plus 3 squared and so on, 1 cube plus 2 cube plus 3 cube and so on. We get the formula that for each of them we come up with the formula that we don't go through the same way that we did it for 1 plus 2 plus 3 plus 4 plus 5. And we are going to do that in the coming lectures, and we are going to start from scratch, meaning that we start from ground zero. We are not following any kind of identity, so-called, or anything. We start to make observation, and then based on that observation, we collect data. Then we put that data into a chart to organize it. Then we seek for pattern for each of them. And that produced for us a fascinating formula for each of them. The formula for each of them are different. Okay, then all this that I have said, I have put it in writing, and I'm going to put them on the board, bulletin board, and stay out of way so that we can go over them together, and I'm going to zoom it, if I may. Okay, let's start with the first one, if I may. Okay, looks like it's zoomed good enough. Now, here what we are going to do, we are going to find this sum of this series, which is a partial sum of infinite series. So we are going to find out of them. So as I have written, I read it for you, come up with some mathematical formula for each of these finite series. And, and the intention is to what? To discover some kind of formula for each of them, for this one and this one and this one and so on. So this is the goal. So let me go now for the second one. Sorry for my primitive equipments. So that should be zoomed good enough, hopefully. Okay, let me go over them. By the way, let me cover this one so that we can go one at a time. Now here, we are given this sum, 1 plus 2 plus 3 up to 100,000. As I have already said, to sit and add them, it takes you whole day long. So we take for part of it, let's say from 1 to 5, and see what this is sign for observation. We make some kind of observation and see if what kind of clue that can give us. So we notice that 1 and 5 is 6, 2 and 4 is 6, 3 and 3 and 6. So we have 3 sixes. So from that, as I already mentioned, we can come to the formula, but I'm going to do it another way which is easier to comprehend themselves. So what I do here, 6 and 6. So it looks like we have succeeded to change the addition into multiplication. So what I did, I wrote 1, 2, 3, 4, 5, and I wrote it also 5 under 1, 4 out of 2, and after that I noticed that I have 6 and 6 and 6 and 6 and 6. Fantastic. So it looks like I have succeeded to change the addition into multiplication, because multiplication, as I have already mentioned, is a repeated addition. So we have 5, 6. But 5, 6 is the summation of all this. Is that right? Which is 30. But that is not we are after. This is what given to us. 1 to 5, not 2. So no problem divided by 2. So it's 5 times 6 divided by 2 give us this summation from 1 to 5. Now, does this one work for 100,000 that we said? All right? Does it work for that one? So I have come to this formula. So that gives us the formula of n times n plus 1 over 2, where n is any given natural number. All right? Now we can now apply the mathematical induction to prove, that is justification, that it will work, this formula that we discovered, n times n plus 1 divided by 2, will work for any given natural number, any given whole number. In our case, it will work for 100,000, guaranteed. Even 1 million and 100 million, that will work. So we came up with a very fantastic formula. Okay, then, for the next lecture, I'm going to talk about, let me put that one up. For the coming lectures, not just next one. I'm going to come with formulas for this and this and this, and we know that they are not following the same procedure, so we have to do different way to come up. But the formula that we are going to find for each of them will apply also for the first one. It's a kind of a very nice discovery, and we do it from ground zero. Okay, then the other thing I would like to mention in closing is this, if I may. Now, the other thing I would like to mention in closing this lecture is that if you want to add this sum, you said this is the formula. But k starts from 1 to n. So the question you ask, what about k is not starting from 1? What about if it's starting from 10 or 100? So we want from 100 to 100,000 to add, not from first. Well, it's very, very elementary arithmetic you can do, and that is what you do. You go, suppose we want from 10 to 100. You see that? Not from 1 to 100. So you go from 1 to 100, that we know we have formula for that. You see that? Then we go from 1 to 9, again we have formula for that. And then we subtract from 1 to 9 from 1 to 100, and what we are left is from 10 to 100. You follow me? So this formula, in other words, we can use it for k, any natural number. Not necessarily, does not have to start from 1, in other words. Okay, then let me zoom it back. Okay, then I thank you for watching, and as always, I wish you all prosperity and good health and happiness, and don't forget to watch the other videos coming, and I wish you again for the second time good health, and please stay safe, stay healthy. So long.